Hello, everyone, and thank you for joining us this evening for our fourth Radiology and Fellows Journal Club. I'm going to start by introducing our hashtag where we continue to follow the conversations online. So please retweet or ask questions after the sessions on this hashtag. Okay, so my name is Judy Gitoya from the IU School of Medicine, and no financial disclosures. And we still have two forums. One is the triberadai.club, which intersects scientists and radiologists who want to keep discussing this. And the other one is Engage, which is our ACR resident and fellow section forum where you need to have registered and be a radiologist or a resident to be able to participate there. Thank you again to the Advisory Council, always helping me on the back end. And jumping into our session today, we are reviewing this paper that was published in the JACR titled Deep Learning in Radiology, does one size fit all? We were unable to get Bradley Erickson, who's the author of the paper, to be in our panel today, but hopefully we'll hear him in the near future. But we have very able people. We have Dr. Kathy Andrew, and I'm going to let them introduce themselves because it's a good chance to talk about their work too. Alexandre and Tom Davenport, and this is an interesting mix because we have someone who's, two people who are very technical, and Tom who is, coming in from a business point and very, just to give a bigger picture. I thought that would be interesting. And then we'll have some time for discussion and questions. We are recording this and they're listed on the ACR YouTube channel, so you can go back and watch the previous sessions. And I wanted to give a shout out. So Tom wrote this paper with Keith Dreyer, who hopefully we'll see in our future webinars, discussing if artificial intelligence will change radiology, but it won't replace radiology. So this just recently got published on the Harvard Business Review and would be an interesting article for people to review. Also, Dr. Matt Lundgren spoke at the SIR meeting with a keynote for artificial intelligence in radiology. I thought it was an interesting talk, and I'm going to retweet this, but I encourage folks to listen to it because I think you'll see some of the recurring themes we've been discussing on the Journal Club, and it's also a good time for you to review and kind of track what you're learning. And so, as always, I'm always open. We're always open to feedback. We've gotten residents who reach out to us because they want to do more. Please continue giving us suggestions of improving this Journal Club. Follow us on Twitter and keep continuing the conversation. And so I'm going to hand over to Dr. Kathy Andrew to start us off with a summary of the paper.
Hi, thank you, Judy. Let me get my screen set up here. So my name is Kathy Andrew, and I've been involved in medical imaging informatics, image processing analysis, and data science for a quarter of a century, so longer than some of you have been around, at a time when we didn't have computers to make things such as deep learning clinically relevant. I'm hearing typing. Can whomever's typing please mute their computer? That would be great. Thank you. And currently, I am at the MGH, Massachusetts General Hospital, and Brigham and Women's Hospital Center for Clinical Data Science. And Judy asked me to review the article by Brad Erickson on deep learning in radiology, does one size fit all? And, this is a very nice article talking about some of the basic steps that are involved in doing deep learning in medical imaging, and also identifying some of the limitations that you need to be aware of if you do this kind of activity. So what I'd like to do is discuss some of those enabling factors really, really briefly, and then hopefully we can have a discussion afterwards. The enabling factors, the existing limitations, and then we'll talk about some of the system components, some of the example architectures and terms. They discuss data amounts. How much data do you need? So we'll hit that topic briefly. And then what does deep learning systems see, in quotes there? And then I have some discussion points to end. So Deep learning, as you may be aware, is a subset of machine learning, which is a subset of overall artificial intelligence, and it's based on, it's been around mathematically for many, many years, based on the notion of how the human brain actually learns and how neurons take inputs from our sensory organs, such as the human eye, and do something to it, and then send it on to neurons down the chain, and how the combination all of those inputs and whatever the neurons are doing creates a learning system inside our human brain. The idea here is that we are using mathematical algorithms to simulate that, sort of, not like the way a bird flies, but maybe how an airplane. So a little bit different than how the human brain learns, because A, we don't understand it completely, and B, it may not be as efficient mathematically. So deep learning algorithms learn features that are, if we're talking about an image, that would best predict an outcome. And they do basically two types of things. The first type of thing that a deep learning or even a machine learning algorithm can do is to detect something, presence or absence, just saying yes, no, is it there, binary decision. For example, is a tumor present or absent in an image? And the other thing that it can do is classify and sometimes localize. So classify, is it benign or malignant, and point to it, where is it? So contrast this with what you know about the older technology, which is computer-aided detection. In that type of tool, what's being used are human-defined features. So a lot of the same features that are being calculated inside a deep learning algorithm, things like looking for edges, looking for differences in contrast, looking for texture, shape, and size, those types of things that you as a radiologist are actually doing when you are interpreting an image. In CAD, we actually had to put in those algorithms to look for the basic features that we thought were important in identifying a problem. What deep learning and machine learning algorithms do is they do that by themselves. They're data-driven, not human-defined feature-driven. So they look at the data, compute lots of different things, and then make a decision based on the data itself. So you may be gathering that this is very, very computationally intensive. And as such, one of the enabling factors that has come along recently is a huge advance in compute infrastructure. We have graphics processing units, GPUs versus CPUs, which are in your traditional computers. And these are able to really designed actually for machine learning types of things, deep learning types of activities. They do things in parallel and have many, many operations per second. And typically these devices have lots of memory on board. So you see this is a DGX1, 8 GPUs in there, the copper. And each one of those is a highly, highly computationally excellent computer. So the other thing, it's not just technology that we've seen advances in. We've seen advances in the algorithms themselves. So just to differentiate here, deep versus machine learning, typically for machine learning, you have some input, you have a hidden layer that's doing all the mathematical magic inside, and then the output piece. For a deep learning algorithm, as opposed to a traditional machine learning algorithm, you have multiple or many hidden layers. What we've seen advances in from the algorithms are in the activation functions, as mentioned in the paper, and what the activation function does, where the red arrow is pointing. So you have on the left side of the lower diagram are inputs, weights, and then those outputs of those weighted sums are summed and then passed to the next layer. And how they're passed to the next layer and how much and what amount is based on the activation function. And what we've seen in the advancements of activation functions that are being used in deep learning algorithms have proven to give us very good results, and particularly in medical imaging. So the lower left-hand corner is the activation function that people used in the early days, a sigmoidal function, which really was similar to what people were measuring in terms of how the biological systems worked. But you can see that it kind of doesn't necessarily weight things. What you want to do is weight strong activities and reward those strong activations. So what is often used today are different types of activation functions. In the upper left, you see a ReLU, which is a rectified linear unit. And essentially what it does is if the output of these different layers of a given layer is less than 0, then you output through that activation function 0. If it's non-zero, then you output the input. And this actual activation function then is very useful in giving strong weighting back to things that have a high output from the simulated neuron. So that's another piece. So we've had enabling improvements in compute infrastructure as well as in the algorithms themselves. What are some of the limitations that are mentioned in the paper that we all should be thinking about? Well, one big one is overfitting. And by overfitting, we mean the network learns the specific examples in the training set. So let's say you're teaching a child to recognize dogs, and they're learning different things in their environment. If you show that child only Dalmatians, they'll learn Dalmatians and dogs with spots. If you show them a Labrador, a black lab, they may not recognize that as a dog because they've been trained to recognize that dogs only have spots. So that's an example of overfitting. And you can create this by poor design of your data cohort and not doing a proper training, validation, and test set. So when you have a cohort of data, you need to hold out a test set of data that is not used at all in the development of the algorithm. So you train based on a subset of the data that you have, a large bulk of it. You then tweak the algorithm, validating on another set, and finally you test on a part of that set that the algorithm development has never seen before. And what we're seeing even in industry is some people have access to very little data, and they are unfortunately seem to be overfitting to the data and maybe not using a separate test set. So this is very, very important to have 3: train, validation, and test sets. The other thing that's very, very important is model development. By that I mean number of features and number of layers. And I love the quote they have in the paper, which was an Einstein quote saying, everything should be made as simple as possible, but not simpler, okay? So basically, if you have so many layers and so many features that you're looking for, you're not going to be able to generalize your model to other types of things. So you're going to get very, very good at recognizing all the specific things in your data set, but it may not generalize to other types of images outside your institution, and so on. And so that's one thing that you have to be sensitive to. One way to do this is to do dropout regularization to mitigate this and randomly remove a subset of the nodes during the training, during each epoch. And when you do that, you take away the strength of that particular set of nodes. It gets put back in, but it doesn't get overweighted while you're training. That can then lead to overfitting. And the other thing that, people often have difficulty getting enough data because these require large amounts of data to train these models. One thing you can do, particularly for imaging, is data augmentation to boost the size and the variability of the training set. And by data augmentation, we mean maybe just rotating an image, adding noise to it, stretching it, so on and so forth, so that the algorithm can generalize to the non-perfect image. And you all know as radiologists that we have non-perfect images in medicine. So let's just see very, very quickly some of the system components before we talk about data amounts. And this is a figure from the article that shows 2 very common architectures, the AlexNet, which is what started all the hubbub about deep learning and being able to recognize cats and dogs on the internet, and ImageNet here. And you can see there's on the left side, you have input, and this may be images, and then you would have output on the far right. In between, you see conv, C-O-N-V. These are the convolutional layers where mathematically you're doing essentially filtering and different feature detectors here to pull out what are the features in the data. If it's an image, what is the texture? What about the boundaries? Are there contrast differences? So on and so forth. And those are done in the convolutional layer. Then you see a pool. That's a max pooling layer, and that's essentially like a compression function where you're taking the dimensionality, because if we're talking about one chest X-ray, that's 10 megabytes, typically 2,000 by 2,000 rows by columns. You would then do a pooling layer to reduce the dimensionality of the problem, and then you repeat and so on. And then typically you have fully connected layer at the end where every node is connected to every other node at the end. And that's just an example architecture that people have been using. Here are a couple of others that we've used. UNet is an example, and you see the shape upper left there. It is in the shape of a U. And the benefit of this type of architecture is that it really goes down into detail of the features and then back up into sort of more global view of looking at the features in the data set. So, for example, you may be looking at, again, edges as an example, but going back up, you're looking at the whole view, the global or gestalt view by using a UNet. We've used ResNet to do things like automatically label the spinal vertebrae, the discs, and then to then go forward and say, is there stenosis right, left, or central foraminal stenosis? That's a typical network that we've used. And GAN, generative adversarial networks, are a very interesting thing that we've been looking at. And the concept here is that you have a real image, let's say as our example, and you try to make the algorithm mathematically fake the algorithm that you have constructed an image, and it can't tell the difference between the real image and the image that you have created. And there's some very interesting things that we're doing with GAN. People are using these for trying to reduce radiation, for example, and see if we can do things with low dose CT using this type of network. So that's the system architectures. What about data amounts? How much data is required? And the answer is it depends. It depends on a number of things. One is, how variable is your data? If it's very homogeneous, then you may not need a lot of data. Are you doing supervised or unsupervised machine learning? Typically, if you're doing supervised machine learning, you need to have the annotation or the label or the answer, if you will, to what's going on in the image, and often that's gotten by the radiology report. If you're doing unsupervised, you have no idea what's in the image, and you just let the data and the mathematics figure out what's going on. And in those cases, you tend to need thousands of examples to be able to do this. The other thing that we're finding is, how good are your annotations? So if you have very, very good annotations, we're finding that you can get away with less data. And it also depends on the task. If you are doing things like trying to find stroke in a head CT, or if you are trying to segment out, say, a liver, we're finding certain tasks are easier to do with less data, or you can do well with less data. So it really all depends on how variable is your data, what type of algorithm you're doing, how good are the annotations if you're doing supervised, and what is the task. And some of the mitigations for not having enough data is that data augmentation that we mentioned, as well as doing something called transfer learning. And here is what a lot of people are doing, starting with an already trained model, such as the AlexNet that we saw the architecture for, and going forward and then training it on the data that you have. And the concept is that you're teaching a child how to recognize dogs. Next time a cat comes along, and our brain is so fantastic that they may initially say dog, but then they realize it's a little different, and they can build on the learning of trying to recognize dogs and now also recognize cats. And it's an interesting area that people are starting to do to try and mitigate the fact that medical data and examples, particularly if something is very rare, are hard to get. And then lastly, before we get to the discussion points, what does deep learning systems see? And that is an interesting piece. I think a lot of people are saying that deep learning algorithms are a black box. I tend to disagree, but one of the ways that we can help us understand what's going on inside a deep learning network and what the computations are doing are a couple of things. One is we can place features into an image or remove features from an image and then assess the performance to figure out what are the important factors that are in the image. Another thing we can do is convert the network weights into a decision tree, like if-then decisions, and you learn what are the most important features that are helping us or the algorithm to come to a particular decision. And the last is attention maps and saliency maps. Attention maps kind of follow or look where the computer is looking, much like if we were to do eye tracking of a radiologist, where are you looking? And saliency maps, again, what and how important is that piece? And this is just a heat map, courtesy of colleague Safwan Halabi at Stanford, from our RSNA Bone Age Challenge that we did this past year at RSNA. And I think it's reassuring if you were a radiologist, because if you're doing a bone age interpretation, I think it would be encouraging to see that the computer is looking where you might look. You're looking at the carpal bones, you're looking at the joints and so forth, and that's how you are telling what the physiologic age of this patient is based on their bone development. So those are a couple ways that we can figure out what does deep learning see. And finally, I put a couple of discussion points, and I don't know, hopefully we'll have some time to talk about them, but I think this was a great article that went through some very important points. I think data cohort makeup is something very, very interesting and very important to think about. And a couple of questions I have for you to think about. Why are convolutional neural nets best for images? Why do they typically use 3x3 kernels for many of the types of things? A discussion around, is deep learning really a black box? And finally, what does deep learning mean for radiology? So I'll stop there.
Thank you, Kathy. We can move on to Alex.
Okay. So hello, everyone. Thanks, Catherine, for this excellent talk. I'm Alexandre Cadrin. I'm a Canadian radiologist with a technical background in computer engineering. I started my deep learning journey quite recently, about 2 years ago, mostly with a very practical and hands-on approach, using online courses as Coursera and FastAI, and by participating in different machine learning challenges, including the recent RSNA Bone Age Challenge. About the current article, I think it's a great summary of the major technical aspects about deep learning for those who are interested to apply it to medical imaging. I'll try to share my own cross-domain perspective to help you get some visual insight about these complex technical concepts. First, deep learning is a recent subfield of machine and representation learning. The recent developments in deep convolutional neural networks for computer vision and the developments of recurrent neural networks for natural language processing are probably the main recent advances driving most of the public attention around AI. I'll take more time about deep convolutional neural networks. In 2012, ImageNet was introduced as probably the first network in ImageNet Challenge that is considered the first public deep convolutional neural network. Since then, we can say that deep CNNs are used very frequently to solve many computer vision problems in many different fields of application. A convolutional neural network is based on successive mathematical layers used to transform progressively spatial information from an image to semantic information associated to the content of an image. The basic building block, as Catherine said, of CNN is based on the combination of a convolution layer, then a non-linear activation layer, and then a pooling layer. The convolution layer will apply different learned mathematical filters to the original image to extract automatically low-level meaningful features. For example, on the first convolution layer could extract vertical lines or maybe a focal red spot from this image. After a nonlinear activation layer like a ReLU, this spatial information extracted will be downsized by a max pooling layer to pass the feature to the next convolution layers. Ultimately, like we saw with Catherine's talk, at the highest level of the network, the feature extracted by the different stacked convolution are considered more abstract features and can be mixed together in a series of fully connected layers to determine a final class activation with an associated probability. ImageNet is a very large visual recognition challenge that's using about 1 million images for training. Since 2012, many different CNN architectures were introduced with ImageNet, and many of them improved the state-of-the-art performance on the ImageNet challenge. AlexNet was initially improved significantly the baseline classification results. Then in 2014, GoogleNet introduced a new architecture also called Inception that is extending at the same time the depth of the network and the width of the network to improve the performance. Also, like we saw, the same year VGG introduced a simpler architecture using progressively larger number of convolutional filters to extract even more features. In 2015, the ResNet architecture was created. It integrates a new skip connection between all the layers to allow, if needed, the flow of the original image or the flow of less formatted images inside the network. This technique permitted a very efficient training of even deeper networks that could extract even more complex features. Generally, in computer vision, not specifically for medical imaging, we can define the basic task in 3 categories. The first one, and probably the most popular using deep learning, is the classification task. This task simply identifies what is represented on an image. The result is usually defined by a class or category and an associated probability. For example, on this chest X-ray, a classification network could output a classification result of consolidation with a predicted probability. The detection task adds supplemental information about the location of a detected anomaly in the image. This information is usually represented by a bounding box coming from the algorithm that locates the anomaly in addition to the class and the probability. Finally, the segmentation task outputs usually a contour, also called a segmentation mask, that delineates a feature or anomaly in the image. This contour can be used to quantify the size or the volume of an anomaly for further follow-up or research purpose. Compared to classic medical imaging analysis, a deep CNN can be considered, as we saw, as a generic and automatic feature extractor for all the computer vision tasks mentioned. We basically just need to add specific network layers after the base CNN network to apply a specific task. For example, we usually use a fully connected cascade of layers with a softmax layer for classification. So we get the classic architecture like ResNet or VGG, but we could add a different bounding box regression layer at the end of the same CNN to do a detection task. We could also use a fully convolutional decoder for segmentation, like the UNet architecture is partly a fully convolutional encoder and decoder. Let's talk about the dataset division. Usually, to allow the training of a network and to measure its performance, we need to divide the entire dataset in different randomized subsets. Most of the data is available is usually included in the training subset. In supervised learning, this subset is basically used by the network to learn by experience from the known labels. The weights of the networks are updated after each learning iteration during the training. In practice, we also use a validation subset to measure the performance dynamically during the training. But in this case, the weights of the networks are not updated. So there's actually no applied learning from this subset of data. Finally, when the training is finished, we measure with the test subset the final performance of the network. This test step is ideally done just once to prevent overfitting of the test data. These different steps are very important to ensure that the network is able to generalize on never seen example instead of just memorizing the training cases. To measure the ability to generalize on unseen examples, machine learning is using a very important assumption that we need to understand when we read a deep learning paper. All the examples from the entire data set and the subsets need to share what we call the same probability distribution over all the input variables. In medical imaging, the main variables that we need to consider are basically the machine vendor, the imaging protocol, the pretest probability, the prevalence of the disease, how we define the ground truth labels, and the patient demographics. It's very important to mention that this research assumption is usually not met in clinical practice. A research performance claim is usually not transferable by default to a local clinical practice. For any research in radiology, it's our job as radiologists to evaluate the transferability of the results to our local population. But this job is probably even more important in machine learning because the training algorithm is mathematically tightly optimized and tested for a specific probability distribution. Small changes to any of the distribution of any of these variables could have very unpredictable results on diagnostic performance. So I'll have some overlap with Catherine talk about these visualization heat maps. So, but like she said, some say that deep learning is a black box, and I really agree that it's not exactly true because there are many ways to visualize the information in the network. I'll show some examples also. The most frequent image is the heat map image, and like Catherine said, we can see the attention of the network when predicting a class. This type of image is showing the density of activations at the end of the CNN. So the value is then mapped to a color code to localize the activated regions on the image. For example, we can see exactly like Catherine said that we see the carpal bones are activated and the epiphysis to predict the bone age. What does the network see? We can see from this type of image that this type of image is showing the low-level activations after the first convolutional layer. Each square represents a different filter learned by the network. So basically, we can understand that this network is able to extract vertical lines, some horizontal line or oblique lines from the image. It can also extract focal color spots that could be used further in the network to predict a class. With these low-level filters, we can also develop an intuition about the concept of representation learning with higher level features. At the second layer of the same network, this network could potentially combine a vertical line with a horizontal line to detect, let's say, a corner. Then at the third level, we could combine different corners to detect a square and so on. So that's the intuition why a deep network can extract complex and abstract features. If we go at the higher level of the network, we can also visualize the result of the weighted sum of all the activations to create what we call an activation vector at a specific position. This very nice work was recently done by Chris Olah and his team, and they were using a Google Net network trained on ImageNet. That's interesting. That's interesting to see that from our own perception, this gives us a visual intuition of what the network actually sees. The image, this image was generated using ImageNet with an algorithm called TSNE. It's based on an unsupervised learning algorithm that is creating 2D clusters of the high-level features extracted by the CNN. We can then use these 2D coordinates to group the similar images together on a single panoramic image. Applying this algorithm on a medical imaging dataset could be possible and could also generate a very rich global image by grouping different images by diagnosis similarity. So the last part of my presentation is focused on the main question of the article: does one size fit all? First, let me introduce this chart that is used by data scientists when training a deep network. This chart is also frequently reported in machine learning papers to show the accuracy of a network according to the number of training iterations. One epoch is usually defined by one training iteration of the entire training dataset. It shows that the longer we train the network, the better is the accuracy measured on the training dataset. But for the test or the validation dataset, there's actually an optimal point where the performance starts to degrade. After this point, the learning process is actually overfitting the training data. Conceptually, it's the point when the network is mostly memorizing the training dataset instead of extracting meaningful features. This second chart shows the ability for deep networks to scale the performance in relation to the amount of data. Compared to classic machine learning, deep learning performance improves very slowly initially with small amount of data, but then steadily improves when scaling the amount of data. The final performance plateau is usually higher than the more traditional algorithms with a large amount of data. The explanation behind this chart is related to the higher number of weights and parameters needed to be properly trained with deeper networks. When these weights are properly trained, the level of abstraction can be higher to get a better performance. This chart gives us a visual insight to answer the main question: does one size fit all? The horizontal axis shows the capacity of the network that is basically related to the size of the network. Informally, a model's capacity is its ability to fit a wide variety of functions. Models with low capacity may struggle to fit the training set, but models with too high capacity will fit too easily the training set, but with a side effect of having a very large generalization gap on the validation dataset. For any specific problem, there's an optimal network capacity that we need to find to get the best performance on the validation or test dataset. The effective capacity is actually quite complex to find and is mostly dependent on many hyperparameters, including the network depth or the type of layers. Roughly, as a rule of thumb, we can consider the deeper the network, the higher the capacity. I'll finish with a real example of this plot. This example is plotting different model architectures according to their size and the reported performance on ImageNet classification. We see on this chart that there is really an optimal size of networks defined by the number of parameters and the number of operations to get the best accuracy results. At that time, ResNet and Inception architectures were the most optimal networks for ImageNet. So in conclusion, I think finding the optimal network architecture with the optimal training hyperparameters is probably one of the main technical and experimental challenge when applying machine or deep learning on a specific problem. So that's it. We can move on to the next panelist.
Unfortunately, our last panelist was not able to join us, so we're going straight to the question section. So the attendees can type the questions as usual, or we can go back to Kathy's points for discussion and start there as people type in. So I hope this is a really good presentation so that when you read any paper, I know the JCR published a whole AI paper or journal on many papers. So this will start helping you to understand when you're reading through papers. And I wrote some of the questions from, some of the discussions points from Kathy. And I think one of the issues we could talk about is, what does a 3x3 kernel mean? I think that was good.
You're asking, well, what do I mean by why 3x3 kernels? So it's really the size of the filter that's looking for different features. And the reason why I think 3x3 filters are often very important is when dealing with imaging, and why convolutional neural nets are best for imaging is because it does go back to the way the human eye sees. The human eye is very good at picking up edges or differences between an object on a background. And what we're doing is looking at local or neighboring pixels. And often when 3x3 kernels are used, we're looking at what's called the nearest neighborhood of pixels around a given pixel. And that convolutional operation takes into account that filter. Alexandre mentioned in his great talk that you're looking for different low-level or local features, like an edge, a vertical edge, or a horizontal or oblique edges. And these are often well detected in an image using something like the local nearest neighborhood in an image. If you use a larger kernel, then you may miss subtle features in an image. Now, having said that, there's sometimes when a larger kernel is useful because you wouldn't want to be picking up noise, or, for example, in an image. But I guess that's what I was getting at there. Does that answer the question?
Yes. Alex, do you have something else to add?
I can comment about the kernel size. Actually, the 3x3 kernel size is the most frequent used kernel size, but there are, I don't know if you see my slides right now, but there are some architectures that are actually using different kernel size, like the GoogleNet or Inception architecture is really harnessing the power of different kernel size. When we say there is a larger width of the network, actually it's we have like parallel nodes using different kernel size, like 1 by 1, 3 by 3, and 5 by 5 kernel size. So this way we can probably get more adaptation to more problems, more different problems, where we need to catch the information in the larger local spatial information. So we don't really know why the 3 by 3 is the more frequent. Probably it's a mix of we're using most of the training are using the training from the ImageNet, and also there's probably a reason about the computations done. Probably the 3 by 3 is like more optimal for to get a very fast computation with GPUs.
Yeah. I'm not seeing any more questions being asked, so I'm going to ask bring up another point Kathy brought up, which is the data cohort makeup. And I think this is a big area for radiology to give an input. Could you make a comment about bias and errors that you've seen just because of the data composition and what you're doing, especially when you're starting to look at, when you're looking at a problem, what should you be thinking, like the practical steps?
Sure. I think I'll speak to our experience and happy to hear Alexandra's experience as well. You don't want to use pristine images when you're in your training set, because that's if you want to have it generalized or to use it in the real world. Because as you know, we don't have pristine images, and sometimes what I'm seeing are people will eliminate or exclude certain images from their set. You also don't want to use typical of doing any research study. You want to have a broad spectrum of everything from normals, very subtle, all the way to not so subtle. So if you're using just strokes that you can see on an image from across the room, then that's what your model is going to be trained to and learn to recognize, and it won't recognize subtle. So you need the broad spectrum of things. What we're finding is, for many cases, we want to have normals, and we're using about 50-50 in terms of, what is the normal image versus what is a finding type image. But, we did an example of looking at stroke, building a model, and trained it on images that were from our MGH set, and totally different vendor and different protocols and so on and so forth, and then tested it on the Brigham set, and it did very well. And I think that's because we put some thought into the data cohort. Now, having said that, you may have only certain access to what you have, but I think you can generalize and give variability to the data set using some tricks like data augmentation and so forth. But I think that's very, very important to think about that. Having normals, we're finding using about 50-50, and I don't know what Alexandra uses, but often we're doing something like 70 or 80% to the training set, and then 10-10 to the validation and test set. But I think your data cohort makeup is important, just like in any clinical study, where you want to have the whole range from no disease to very subtle, all the way to very severe or very obvious.
Yes, well, I totally agree that the choice of the dataset is very important, and the variability of the dataset is also important. Concerning this slide, that's what I meant by these all the cases are sharing the same probability distribution. I agree that about the division, or like, let's say 80-10-10 or 75-10-15. That's usually we want to use most of the cases in the training data set, because this is the part that is improving the learning and the weights of the network. What's interesting is that in some problems, if we change the size, the network can actually learn different features, and then we can ensemble these different learning, these different networks to even improve the final result. And there's something I want to underline also is the difference between generalizability and transferability when using deep learning, especially in medicine and radiology. As I previously said, most of the performance results we observe on a research dataset are not directly transferable to clinical practice because the probability distribution of data isn't the same. So if we want to safely use an AI algorithm, let's say that we're assuming that it's cleared by the regulators, I think we need at least to test it locally with our own local data to confirm the performance. If possible, ideally, we could retrain a regulated network with transfer learning on our own local data to get the best performance possible on our data. I understand that these local validation or retraining steps can be very hard to implement widely across all healthcare centers. But in my opinion, I think this transfer gap explains much of the observed difference between the hype of AI and the future real clinical productivity of AI applications.
Yeah, I totally agree with that. And sort of the concept that people are thinking about is that you have a model that someone else has developed, but you're absolutely right. You would then take it from the cloud and use your data to, in a sense, to refine it for your particular patient distribution, the distribution of the data, and so forth. So I totally agree with that, and I think this is an interesting problem that I think the FDA will be struggling with because the model has some intellectual content in it, and then the data itself adds to it. But you could start with a base model and do some transfer learning from that. It'll be interesting to see. I don't think we know how it's all going to play out, but I agree with that.
Yeah, right.
We have some questions coming in from James Condon. Thanks for joining us from Australia. In terms of input, are there differences between using multiple patches from different planes of a CT or MRI versus 3D reconstructions as input?
Yeah, I mean, I think, yes. So for example, what we've been able to do is, I'll give you an example, differentiating sort of body composition. So by looking at L3 level, just one axial slice, and looking at the amounts of muscle versus subcutaneous and visceral fat. And it gives a good representation of what's going on for body mass that people are using here for other research projects, things like assessing whether a patient will do well in surgery or general health based on body composition. But we're in the process of looking at whether 3D segmentation of muscle and fat is a better representation. And we don't know the answer to that, but one might think, yes, that it is. It's more computationally intensive, and we're looking at how we can grow the maps to 3 dimensions. There are certain other types of examples that one might do where you really do need to look at 3D, for example, looking at fluid in the body, because it will have different representations in different parts of the body. So, looking at 3D, I think is interesting and would be better. But oftentimes we only have annotation in one slice, and you have to use other methods such as region growing and so forth to expand that to 3 dimensions.
Alex, do you have a comment?
Well, from my radiologist experience, I would say that the 3D information is quite critical. That's part of the learning of when we learn to become a radiologist. We learn to think in 3D when we move all the slides, all the images from a CT scan. Our brain really get a representation of the 3D, and this definitely improves our own diagnosis performance. If we would just see like CT images in 2D, like independently from each other, we would really degrade our own performance. So there's definitely also an improvement that we can get with training a network in 3D, but that's that's harder because most of the networks that we're using, especially the CNNs, are often pre-trained on larger databases, mainly ImageNet, and this is a 2D data set. So there's not much 3D data sets known, very large 3D data sets to train all the weights of very deep networks. So usually we need to train from scratch in 3D. So it's pretty hard with a small amount of data.
I have another question from Justin, who asks, can you talk a little more in depth about the process of saliency map development and production, namely the heat map as the native image overlies, for example, the RSNA bone age or CheckNet is strong with the C-suite and grant review folks who need to see the reality?
Yes, I can talk a little bit about it. Well, like I said, the heat map is showing the density of activations at the end of the CNN. So if we have a lot of activation at the end of the CNN, the density number will be higher, and then there's a color code that will be output from this density. So then we can just show both images from the color code with a layer of the original image to generate this heat map. So that's basically the way to do it. There's a lot of code, generic code on GitHub to do this this step if someone want to do this.
Kathy, do you have a comment?
No, I think that covers it. I mean, I think it's it's one of the reasons why and it sounds like we all agree that people are saying deep learning is a black box, and I'm disagreeing a little bit there. I think there are things that we do know about it, and I think it would be reassuring to see that the high activation areas are in fact the areas that you are picking out in image to make your interpretations, and hopefully that would be a little bit of reassuring. I would like to sort of turn the coin a little bit and say, in terms of black box, often it's very difficult to get a radiologist to articulate what in fact they are picking up in an image to make the diagnosis. And so we have to think about that they're not necessarily a real scientific or objective metrics that we can apply that say this is what a radiologist is doing, other than their many, many years of understanding of anatomy, pathology, and interpretation of the image and experience. So, I think there's a little bit of gestalt that goes on in what a human radiologist is doing. So maybe that brain is a little bit of a black box itself. I'm interested in what people think this means for radiology, and just a comment that I think some of the applications we've seen are really sort of narrow applications or narrow AI or narrow machine learning, and that, as you know, as a radiologist, what you're looking for are many, many things in an image, and often what a lot of the applications that we've seen out in startups and so forth are picking out, one thing where, maybe they're very good at picking out lung nodules in an image, which is great, and help with screening CTs and so forth, but may miss entirely the pneumothorax or the PE that could have significant morbidity and even mortality if missed today urgently, versus something, the lung nodule, that may have morbidity, mortality, but further a longer time away from today. So I think there are a number of things that, in my opinion, that I don't see this replacing a radiologist. I think that what we're doing at the center, which is focused on taking our machine learning and deep learning and AI algorithms and actually translating them back into the clinical arena, is that a lot of the attention has been put to detection and so forth, but we're also seeing that these techniques can be used really at any point in the imaging chain and help with things like coming up with the optimal protocol, help with creating reports at the end and doing those automatically, and helping with sort of mundane things like optimizing scheduling of an MR scanner so that it doesn't sit empty. And so I think it's something that can be used at a lot of different points in the imaging chain, and we see it as like a clinical decision support tool for the radiologist that will work with the radiologist and be used as an assist, not replacing the radiologist. So I don't know if people have any comments about that.
Yeah, so I'm going to let Alexandre comment on that, because he can speak on audio, and hopefully the audience is going to type in what they think on the chat, and I can read some of the interesting things. What do you think deep learning means for radiology?
Well, basically, we have two scenarios that are proposed or claimed about the augmentation scenario and the replacement scenario. It's very unpredictable to know what will go on. Everyone want to predict its own opinion, but the reality is the deep learning research is very, very moving at a fast pace, and right now we are basically limited by the amount of data, and especially the amount of labeled data that we can use. So probably the reality is a mix of both. I definitely see a lot of tasks that would be very useful in an augmentation scenario, but probably that there are some more straightforward tasks that we're doing in radiology that could be simply replaced. And I think it's a matter of adaptation. The classic question that we ask is AI a threat or an opportunity to radiology? And the answer is pretty clear for me, that if we decide to fear AI, it will likely become a threat. But if we embrace AI and adapt to the changes in the future, it should naturally become an opportunity, mainly to improve the quality and accessibility of our services. So consequently, I think most of us should become lifelong learners and probably students to adapt to any situation in the future.
So a few comments. Shaheen commented that no one has talked about image acquisition, and he sees a huge potential on that side. In fact, that will be the paper we'll be discussing on our next Journal Club. Justin says the application of AI to pre-image data could be a real challenge to the human image interpreter. And James reiterates that radiologists do more than pass pixels visually into a one-word class or number. And so listening to histories and exam, giving advice about the modality are some of the other things we do. And Justin reiterates, even if he said that pre-image data could be a real challenge, he's still very optimistic. So I'm going to ask a question that Shaheen asked. Do you think FDA approvals should have expiration dates for neural networks?
Yeah, I don't know, and I don't think they know at this point. I know there are discussions going on. Yeah, I don't know. We could throw that question back to similarly to computer-aided detection algorithms and improvement in those algorithms in time and changes in the imaging modalities themselves and the quality of the image. I don't know how that's going to play out. I think what was suggested is that you put a model out there and then it needs to be trained locally. I think that may be a methodology for going forward, because you really do need to train it on your systems and so forth. But I don't know what the FDA is going to do in terms of saying you need to retrain. I don't know, Alexandra, do you have any thoughts there?
Well, that's a good question. I think we should probably play it safe in the near future, because the reality is we really don't know how these algorithms will perform in their wide clinical centers, and it's probably very hard for FDA and all regulators around the world to predict this. So that could be a good idea, especially in the near future, to maybe be safe and stop the regulation and fix a regulation date to update it in, let's say, 2 or 3 years, so we can see actually what is going on. Because, like I said, the research is very, very fast, and nobody really knows what will be the future with this.
I know Babe Allen is on the call. It would be great if he typed in what he thinks on this, because I know he's spoken on this from our first journal club. And one last question from the audience, and then I'll give the panelists a chance to wrap up. Dania asked, most of the networks that we currently use for deep learning are based on ImageNet. Can the speakers comment on the technical implications of how will medical ImageNet affect the development of AI tools for medical imaging? And I know the Stanford group recently said that they're working on this with Dr. Feifei, who really is the person who developed ImageNet.
Well, I think the medical ImageNet, the idea there is to provide a collection of de-identified and fully annotated data sets. So I know from what's happening in our group, we probably spend 70% of the time curating data, normalizing it and so forth, and annotating. And that's a real big blocker for many people to have access to large numbers of well-annotated data. And if they are able to provide that through this effort that Stanford is putting through, then that would be a benefit to researchers doing work in this area, I would think.
I think Medical ImageNet is a really great project, especially if all the data sets will be public around the world, because it could really helps all the research communities around the world to access data. What will be interesting to see compared to ImageNet pre-training will be if the actual transfer learning done after a pre-training on medical ImageNet will be more efficient on new, more restricted data sets, because we actually use ImageNet as pre-training, but the low-level filters are optimized for ImageNet, and they aren't optimized for our medical imaging. So if we can train a very large network on a wide variety of images with a medical ImageNet, probably that we will have better results from more local transfer learning with more restricted data sets.
Okay, so I'm going to let the panelists wrap up and give a comment. It's free. They can talk about their work or what they're excited about, or some advice to our attendees. Yep. Kathy,
well, I'd just say that I think this is a really exciting work, and things are happening quickly, and I think it's important for to have clinical acumen involved in what we're doing so that things are clinically relevant and that are useful for the types of things that you all need in radiology. So I think it's really exciting to see the radiology community involved in this work. A lot of the algorithms are, while modifications are some of the advances, the basis of a lot of the mathematical algorithms are not new. So I think injecting clinical acumen into it and having the excitement of the radiology community is very, very important. I think this is going to be useful tools for radiology and all of healthcare going forward. So I think it's a really exciting time, and things are happening very, very fast. And just like we're using machine learning in our phones and so on, I think it will be embedded in a lot of different healthcare systems. So I'd love to see radiology driving this for the healthcare community.
Thank you. Alex?
Yeah, I think mostly the recommendation I would give to residents and radiologists is that we need to really embrace AI as a radiology community. We don't need to fear AI because it will be very there's no use to fear AI right now. We need to create the use cases to move on mostly on augmentation scenarios and to participate in the different researches and to get a better bond with the deep learning research community. I think we should probably get more education in our training, mostly about statistics and probability, and maybe some computer science courses, because these fields form the basis of machine learning, and we really need to strongly understand these concepts to fairly evaluate machine learning papers or machine learning performance claim. So that would be the recommendation I would give.
Okay. Okay, everyone, this brings us to the end of this discussion. I hope you learned something, and considering watching the talk, I think this was a really, really good overview of the whole process of deep learning. We've been tackling sections from our previous journal club, and so this is a good recap, so as you read your articles or start taking a course, you have an idea. One more thing, our next journal club, we're still trying to narrow down on the topic. I think one of the advisory council members suggested one that's looking at image reconstructions. I think that's an interesting area, and so we hope that you'll join us. Thank you again for your time, and we hope to see you next week. And thank you to the panelists too.
Great, thank you, Judy. Thank you all.
Thank you, everyone. Thank you, Catherine and Judy.